Okay, welcome to our discussion on using the velocity equation. During this discussion, we're going to also talk about average and instantaneous velocities. I'm going to show you an example for how to solve for velocity, distance, and time. So let's get started. So as we talk about average and instantaneous velocity, we're going to do it in the context of taking a trip. And the trip we're going to take involves getting on the highway, then driving for a while at a constant 55 miles an hour, stopping to get some gas, and then getting back onto the highway where we drive 55 again, and then getting onto the interstate where we drive 65, and then finally stopping at a destination. So to make this a little more visual, we're going to graph it real quick. And you can tell on this graph, I've got my velocity on the y-axis, time on the x-axis. So this is a velocity versus time graph. So when we're sitting at home, our velocity is 0. So we start off down here, and then we speed up all the way up to 55 miles an hour. Then we stay at a constant 55 for a while. Then we notice, oh, we're running out of gas. So we stop at a gas station. So our velocity goes from 55 down to 0. We're at the gas station for a little while. And then we speed back up to get on the highway, 55 miles an hour again. And then we get on the interstate, speed up to 65. We go to our destination, and then we slow back down to 0. So that's our trip. Now, as we're talking about this trip, we can see that our velocity is changing constantly here, staying constant here, changing again. And over the course of our trip, we have lots of different individual velocities, but an overall average velocity for the entire trip as well. Now, you can tell this average velocity is going to be less than our greatest velocity and more than our least or smallest velocity. It's going to be somewhere in between those two. Now in this trip, we spent most of our time at high speeds and very little time at these lower speeds. So we should expect that our average velocity will end up being closer to the higher speeds than the lower speeds. Now to find our average velocity, the easiest way is take your total distance driven and divide it by time. Instantaneous velocity is your velocity at each individual point along the way. So let me show you what that looks like. So if we were to average all these velocities together, we would get something around here, which is upper 40s mile per hour. So we'd have two options. On our trip, we could drive like this, where we speed up, stay constant, slow down, get gas, all this changing of velocity. Or if we just drove at a constant 48 and never stopped, we'd get at the same location at the same time. So that's our average velocity. Now, instantaneous velocity is going to be different every point along the way. So for example, at this point right here, our instantaneous velocity is 30 miles an hour. At half an hour, our instantaneous velocity was 55 miles per hour. At the 1 hour mark, it was here. At the 2.5 hour mark, our instantaneous velocity was 65. So basically, instantaneous velocity is just your speed at that one time. Average velocity is your speed averaged across a section of time. If that makes sense. Our next slide involves solving for velocity. To do that, we're going to deal with Jennifer and Doug, who are playing paintball, and they want to measure the speed of the paintball, or the velocity of the paintball pellet. So what they do is Jennifer stands about 50 meters away from a tree, and then Doug videotapes her shooting the tree with the paintball pellets, and they can use the video to then find out how much time went by between when she fired and when they hit. So let's get started. First thing I'm going to do is I'm going to write down the things I know and don't know in the problem. One of the first things I notice is that this 50 meters. And of course, that 50 meters is a distance. So I know the change in distance of the pellet is 50 meters. I know this number as well, 0.68 seconds, and that's the time it took, so I know the change in time is 0.68 seconds. And I want to know what the pellet's velocity is, so I'm going to come down here and say velocity is unknown. Now, what do we know that relates these three quantities together? And that, of course, is the velocity equation. Velocity is equal to the change in distance, how far it moves, divided by the change in time, how long it takes to move that distance. So we're looking for velocity here, and our equation is already solved for velocity, so we're ready to plug numbers in and get going. So we've got 50 meters divided by 0.68 seconds. We plug that into the calculator, and we end up with 74 meters per second. And that's our answer. Our next example problem involves solving for distance. In this case, James is driving to the Olympic Game Farm, which if you haven't been is worth a trip. It's up by Squim, to see the wild animals from his car. Now the trip takes 1 hour and 15 minutes, and his average velocity was 50 miles per hour. How far was the drive? Now one of the first things I noticed is I said hours and minutes here, and then hours here. So these units don't match up. I'm going to have to convert these minutes into hours and get this as one time instead of two time components. So we'll deal with that in just a second. So first of all, as always, we want to write down what we know and don't know. We know our change in time is this weird unit of 1 hour and 15 minutes. And we know our velocity, which is here, is equal to 50 miles per hour. And we're looking for our distance. So our change in distance is unknown. Now first, we're going to need to take this hour and 15 minutes and convert it into just hours. So to do that, I'm going to take the 15 minutes and convert it into hours. Now minutes are on top here, so I know minutes are on bottom here, meaning hours must be on top. And I know that there are 60 minutes in 1 hour. So the minutes cancel, and that leaves me with 0.25 hours. So now instead of 1 hour and 15 minutes, I can say it's really 1.25 hours. All right, so now we're ready to get started. Now we got to think what relates to these three ideas: change in time, change in distance, and velocity. And of course, that's the velocity equation. So I'm going to start with v is equal to change in distance over change in time. Now in this case, we're looking for change in distance. We want to solve for it, so we want to get it by itself. And right now it's change in distance divided by time. To get rid of this divided by time, I multiply by time. So I multiply both sides by change in time. Now a common mistake I see with this is students will take the change in time and put it down here and put a dot there. Now this really means divide. Whenever you put a number on the bottom of a fraction, you're dividing it into the numerator. So even though you put a dot here for times, it's really being divided into that fraction. So we want to not put it on the bottom. We want to make sure we put anything we're going to multiply on top of the fraction. So delta t here. And if you multiply this side of the equation by time, you have to multiply this side of the equation by change in time as well. All right. So now this change in time cancels this change in time. I'm going to switch the equation backwards and put a delta d on the left. So change in distance is equal to change in time times velocity. And at this point, we're ready to plug numbers in because we've solved for delta d. And so we can see that the velocity, change in time, is 1.25 hours, and the velocity is 50 miles per hour. Do the math on our calculator, and we find the answer is 62.5 miles. So this is solving for time. And in this one, we're going to look at Andy Riddick, who's a famous tennis player. He's been measured to have a serve of 155 miles an hour. And since the tennis court is only 78 feet long, we want to know how many seconds his opponent has to respond to that serve and return it. So one of the first things I noticed again is that the units didn't match up. I had miles here and feet here. I've got to get those to be the same. I also had hours here, and I want seconds in my answer. So I've got to get those to be the same as well. Now to do this, since I have to turn seconds or hours into seconds anyway, I'm going to go ahead and turn these miles into feet. Now you could just as easily turn these feet into miles, but then I'm having to convert two different numbers instead of just converting one number. So that's how I'm going to start. So first things first, we need to identify what we know and don't know in the problem. In this case, we know the 155 miles per hour. We know that's a velocity. So I'm going to put this here, 155 miles per hour. We also know the change in distance, the 78 feet. So change in distance is 78.0 feet. And we're looking for the seconds, the change in time, which is unknown. Now, before we do this, I'm going to go ahead and convert this number so that it is feet per second instead of miles per hour, so the units match up a little better. So I'm going to first convert the miles. So right now, miles are on top, so I put the miles on bottom, and that means that feet are going to be on top. And I know that there are 5,280 feet in 1 mile. If you didn't know this number to do a few steps, that would be okay. So miles cancel out, and I'm left with feet per hour, but I need feet per second. So I'm going to make another fraction here. And since hours is on bottom here, I'm going to put it on top here so it cancels, and that leaves seconds for the bottom. And I know that there are 3,600 seconds in 1 hour. And then we just do the math. And we end up with a speed of 227 feet per second. So that's our new velocity that we'll use in the problem. So go back to the problem. We have to think, okay, what do we know that relates these three things together? And that, of course, is the velocity equation. It's delta D over delta T. Now, in this case, we want to get delta T by itself, change in time by itself. And here's a common mistake people make in doing that. They look at it and they say, oh, well, I need to get rid of the D because to get T by itself. So they put a D down here, and they divide this side by change in D. They cancel out the D's, and they say V over delta D is equal to delta T. The problem with this technique is notice how T was in the denominator here at the bottom of the fraction, and now suddenly it's not in the denominator, it's in the numerator. You can't just suddenly make that flip happen. So I'm going to show you a better way of approaching this. So the problem here is that the T is in the denominator. Whenever you encounter a T in the denominator, you got to first get it out of the denominator. So the way to do that is simply to multiply delta T on both sides of the equation. These two delta T's cancel, and you end up with delta T V times velocity is equal to the change in distance. Now notice we haven't solved for the change in time yet. It's still here, but we have at least gotten out of the bottom of the fraction. We have one more step left, which in order to get rid of a times V, you simply divide by V. If you divide one side, you got to divide both sides. The V's cancel, and you get a final equation of delta T is equal to the change in the distance divided by the velocity. And at this point, we're ready to plug numbers in now. So we get 78.0 feet divided by 227 feet per second. And we just do the math on our calculators. And we end up with 0.344 seconds. That is the amount of time it would take the ball to travel the length of the court, which is pretty incredibly small. You would have less than 4/10 of a second to get your racket back and get a swing on that serve.